Now that we have seen these recursive definitions of sets, functions, and structures, I want to now talk about a form of mathematical induction or induction that we use to reason and to prove results about recursive definitions. And this technique we call structural induction. Structural induction. And just like we have seen for mathematical induction in general, the point here is that we want to do induction where the base case applies to the basis step or the base case of the recursive definition, and the inductive step applies to the recursive step in the definition. Okay, so I want to show it in particular on the cases of strings and full binary trees, because these are two structures we defined here. So suppose I want to show, suppose we want to prove the result, the P of W for every W in sigma star. Okay, so P is some sort of propositional functions, and I want to show P of W for every string. Okay, just like when we P of n in mathematical induction was some property of n, then P of W will be about every string in W. So using structural induction, we need to show for the basis step, we need to show P of W for the W that is formed by the basis step. Remember that in the basis step, the only string we had there was epsilon. So here we need to show that P of epsilon is true, right? We need to show that P of epsilon is true. And for the inductive step or recursive step, we need now to show P of W by applying it to, based on how we formed the strings recursively. And remember that, I will put it in a different color here. Remember that for the definition, the recursive step was if W is a string and sigma is a letter, then W sigma is a new string that we can form, right? So for the inductive step, we need to follow this one here. So now we need to show that if W is so we need to show here that if P of W is true and sigma is a letter, then P of W sigma is true. Okay, so we need to show that if P of W is true, and this W of course is in sigma star here, okay, W is in sigma star, and we have little sigma that is a letter, then P of W sigma is true. In this case here, similar to before, when I say show that if this P of W is true, this is the inductive hypothesis, right? So I assume it is true for a string W. Now I need to show that P is true for the next string I can form using the recursive step, which is W little sigma. Okay, so let's show actually an example of this. So we have a theorem that says that if I give you two strings, let x and y be two strings, and remember that each one of them, x and y, will be defined recursively. So x is formed by recursive definition of strings and y is formed by recursive definition of strings as well. Then the length of xy, if you take two strings and concatenate them, of course we know that the length of this is really the length of x and the length of y. You can easily verify that. Take any two strings and look at their lengths. Take these two strings, concatenate them, and look at the length of the resulting string. You will notice that the length of the resulting string is the sum of the lengths of the original strings, right? So how do we prove this? Using structural induction. For proving it using structural induction here, we need to think about what is that P of something, okay? So the P here, we need to think about the P, which is the propositional function that we need to think about it as, actually, before I talk about that, let me say that I want to remind you that we have the recursive definition. We know that L of epsilon is 0, and we know that L of W epsilon is L of W plus 1. This is given because we had used this definition, right? By definition, we had given this definition of length. So now I want to show that the length of xy equals the length of x and plus the length of y. We define here P of W to be the statement, or I should not say equal here. P of W is the statement that L of xw equals L of x plus L of w for x and sigma star. Okay, so if you take any x and sigma star, which is a string that's given to you, and P of W is the statement that if you take W and append it or concatenate it with X, then the length of the resulting string is the length of whatever string we had plus the length of the new string that we added. Okay, so this is really the P of W that we need to prove here. And now I need to prove it using the structure induction, and I focus on the basis step. The basis step is that I want to show P of epsilon. What does that mean to show that P of epsilon? I really want to show that L of x epsilon is L of x plus L of epsilon. But L of x epsilon is L of x, and L of x here, L of epsilon by the recursive definition of the length, it is 0, which is L of x, right? So x epsilon is x by the definition. L of epsilon is 0 is by definition of the length. So we have shown that P of epsilon is true, okay? Now we need to show the inductive step. I need now to show that we need to show that if it is true for P of W, then it is true for P of W sigma. So assume P of W and show P of W sigma for this letter sigma. Okay, so what does it mean, assume P of W? It means that the meaning of this is that L of xw is L of x plus L of w. What does it mean to show P of W sigma? Show that L of xw sigma is L of x plus L of w sigma, right? So if I tell you that you can assume that L of xw equals L of x plus L of w, show me that L of xw sigma is L of x plus L of w sigma. Okay, so notice that by recursive definition, L of w we have, so by recursive definition we know that L of xw sigma is L of xw plus L of sigma. This comes from the definition of the length, the recursive definition of the length, where we defined that if you give me a string plus a letter at the end, the length, this is this one here. Let me actually write it again in blue. It's worth writing again. The L of W sigma is L of W plus L of sigma. And this is really 1 here, right? So what we're saying here is that xw sigma, it is xw and there's a letter at the end appended to it. So this is L of xw plus L of sigma, and this equals L of xw plus 1. Okay. Now by the inductive hypothesis, we know that L of xw equals to L of x plus L of w. Right? So we know that L of xw sigma is L of xw plus 1. And by the inductive hypothesis, this is L of x plus L of w plus 1. This is by the inductive hypothesis. And so now we have this, and I can group things differently now, and I can say L of x, this is equal to L of x plus L of w sigma, because this is, again, using the recursive definition of length, this is L of w plus that sigma letter there. And this is really what we wanted to prove, right? I wanted to prove this result here. And that's what we established. Okay, so it's really just focusing on the recursive definition and trying to and doing the structural induction by first showing it for the basis case in the recursive definition, and then for the inductive step to show it for the recursive step in the recursive definition as well. Okay, the second example I want to show has to do with the full binary trees. And just as a reminder, for the base case, a single node with a single tree, a tree with a single node is a tree. This is the base case. And the recursive case is that if you have T1 and T2, you can create a new tree by adding a new root and making these two trees as its children. So this was the definition. I want to give another, and remember the height of a full binary tree, for it was 1 plus the max of the height of T1 and the height of T2. This is the recursive step, and of course h of a tree that has single node in it is 0. I want to define a new function here on full binary trees, which is the number of nodes in full binary tree T. And this is easy. The basis step, a tree that has one node, sorry, not H here, this is N. The tree that has one node, it has one node in it, right? So this is for tree consists of only a single node, and then for the recursive step, I say if T equals T1 and T2, this is the new tree that we form for it, then n of T is really n of T1 plus n of T2, whatever nodes were in these two, plus the new root that we added to it, right? So if I have this number of nodes and I have the definition of the height, then we have a very important result or theorem about full binary trees, that if T is a full binary tree, then the number of nodes in a tree cannot exceed 2 to the height of the tree plus 1 minus 1. Okay, so the number of nodes in the tree is bounded by a quantity that has to do with the height. You should reason about it and think about it carefully, because if we have a full tree that if the height is 3, for example, then you have the root, 2 children of the root, then 4 grandchildren, and so on. This is the maximum number of nodes you can have, and it is bounded by a function, an exponential function in the height. Okay, so you should try this for a few full binary trees to convince yourself that it is true. So how do I show this now? How do I show this using structural induction? For the base case, the tree has a single node in it, right? So in this case, n of T is 1. We know it from the base case of the recursive definition of number of nodes. The height of the tree is 0. We know this from the base case of the recursive definition of the height. 1 is smaller than or equal to 2 to the 0 plus 1 minus 1, because 2 to the 1 is 2 minus 1 is 1. So the base case holds. For the inductive step, now I need to say that assume P of T1 and P of T2 I want to assume that the proposition is true for T1 and T2. And I want to show that P of T1, T2 is true. Okay. What does it mean to assume that P of T1 and P of T2 is true? This means that this assumption is that n of T1 is smaller than or equal to 2 to the height of T1 plus 1 minus 1, and the number of nodes in the other tree is 2 smaller than or equal to 2 to the height of tree T2 minus 1. This is the inductive hypothesis. From this, I want to show that that n of t is smaller than or equal to 2 to the h of t plus 1 minus 1. Okay, so if we look at this n of t, by the recursive definition, it is n of t plus n of t1 plus n of t2 plus 1, right? This is the recursive definition of the number of nodes. We know that this is smaller than, now I can use the inductive hypothesis. I know n of t1 is smaller than 2 to the h of t1 plus 1 minus 1. N of t2 is smaller than 2 to the h of t2 plus 1 minus 1. And then we have the plus 1 here, right? So I can group them here. I can group them and I say this is minus 1 plus 1. This is all minus 1. So this is equal to 2 to the h of t1 plus 1 plus 2 to the h of t2 plus 1 minus 1. Okay. Now if you look at this here, this is smaller than or equal to 2 to the maximum of h of t1, h of t2 plus 1 minus 1. Right. This is always a result that we can make use of, which is if you look at a plus b, let's say, it is always smaller than or equal to 2 times the maximum of a and b. Right. So if I give you two numbers and add them, if you replace the smaller of them by the maximum, then you'll get just a larger number, at least a larger number, right? So this is what we made use of here. So this is smaller than or equal to 2 to the ht1 plus 1 and h of t2 and plus 1, okay? This one here now, what I wrote is, this is 2, sorry, this is 2 here. There is a 2, I missed that one here, right? Because again, this is the 2 here that I put before the max. 2, what is the max of ht1, ht2 plus 1? Remember that this is the recursive step in the definition of the height of a tree. So this is 2 to the h of t minus 1, and this gives me 2 to the ht plus 1 minus 1. And this is exactly what we wanted to prove. Okay? So here I used the inductive hypothesis in this step. This is I used the recursive step in the definition of n of t, and here I use the recursive step in the definition of h of t. And here, going from this line to this line, I really just use this simple fact that if you have the sum of two numbers is smaller than or equal to 2 times the maximum of the two numbers, and this one here, I apologize. Yeah, so this is the 2 to the h, 2 times 2 to the h of t minus 1 equals 2 to the h of t plus 1 minus 1. This is the recursive step here. It's this one, not this one here. And this gives me the result that I'm trying to prove here. Okay?